In previous videos, we have seen that the Bessel equation for any value of nu, known as the order of the Bessel equation, can be investigated using the method of singular series expansions. So you can write this as x to the power sigma, the sum from k equal to 0 to infinity, a sub k x to the k, and this leads to the characteristic exponent sigma to be plus or minus nu. If nu is not an integer, then the plus or minus nu provide us with the two linearly independent solutions to the second order differential equations. These are called the Bessel functions of plus nu order or minus nu order, and they are given by a closed form expression that looks like this: negative 1 to the power m divided by a product of gamma functions times x over 2 to the power of 2m plus or minus nu. So it's a pretty complicated expression, but it's there, and there are plots and tables all over the place. These are called Bessel functions of the first kind. If nu is an integer, then you can show that these solutions are not independent. In fact, you can show that j minus n is equal to negative 1 to the power n jn. Well, there goes your second linearly independent solution. You can no longer have it. Well, the solution in that case is given by what's called the Bessel functions of the second kind, or more popularly called the Neumann or Weber solutions. And they're given either as n or y. I think y is by far the more common way of writing it. So y nu x is going to be cosine pi nu j nu x minus j minus nu x divided by sine pi nu. And you can show as nu approaches an integer, this actually is a completely second new solution compared to the first one. Also, if you want to find y naught, for example, you have to take the limit as nu goes to 0 of y nu of x, because for the case of y naught, that's an even more special case. J minus n simply doesn't exist for that particular situation, because j naught is just j naught. There's only one double root. Sigma equals plus or minus 0, so there's just one double root, and so the second solution is given by this limiting process. Now there are recursion relations that are satisfied by the Bessel functions as well as the Neumann functions or the Weber functions. I'll only write them for the Bessel functions because the similar expressions that you write for Neumann or Weber will be exactly identical. So as an example of how you can use these recursion relations, the primary recursion relations are ones that relate the primes or the derivatives to differences of Bessel functions. So this is useful if you ever want to take a derivative of a Bessel function and you don't want to deal with these monstrous expressions. So this tells you, hey, just take the Bessel function of the lower order and the higher order and subtract them and divide by 2. So that's a very useful recursion relation. Another very useful relation is this. You can show that 2 nu over x j nu is equal to j nu minus 1 plus j nu plus 1. This is particularly useful to get higher order Bessel functions from existing lower order ones. So if I write this in terms of j nu plus 1, j nu plus 1 is going to be 2x over 2 nu over x j nu minus j nu minus 1. Let's use this to maybe show a couple things. So let me say I know J0 and J1. I want to find J3, and I also want to find J2 prime. How will I proceed? Well, to find J3, I'll have to first find J2. So let me do J2 first. By this algorithm, J2 is just going to be 2 times nu is equal to 1. So that's 2 times 1 over x J1 minus J0. And that's going to be 2 J1 over x minus J0. Well, that is a good stepping stone to the next step, which is J3. That's where we really want to get. We want to get to J3. J3 means you have 2 plus 1, so nu is equal to 2 in this case. So that's going to give me 2 times 2 over x J2 minus J1, because nu is 2, so 2 plus 1 is 3, 2 minus 1 is 1. Now that's 4 over x J2, which I know to be 2J1 over x minus J0 minus J1, and so I know the answer. J3 can be written in terms of the J1 and J0. I don't want to waste time simplifying it, but you can do that. So we know J3. What about J2 prime? There you have to use this. J2 prime is equal to 1/2 of J1 minus J3. Well, here again, you have a situation where J1 is given to you, but J3 I just found. So you can put the J3 there, and so that's also known. In this manner, you can really express Bessel function of the higher order with Bessel functions of the lower order and also their derivatives. Now, there are certain properties of the Bessel function that are extremely important, and some of these are called asymptotic properties. Asymptotic means what happens when x becomes large or small. So for large x's, all Bessel functions are going to behave like damped cosines or sines. So it's going to look like 2 over pi x cosine x minus nu pi over 2 minus pi over 4 plus higher order terms. I'm not writing the higher order terms, but they all look approximately like damped cosines or sines. If you look at this cosine term, it's divided by root x. So they're basically damped oscillations. This means Bessel functions will show up very naturally in situations where you have a simple harmonic motion. The ideal case, it will keep going on forever, but you throw some sand in it, or let's say the mass that's oscillating loses mass somehow, either by melting or by evaporating, and then you have these damped oscillations going on. Or if you have air resistance, that's another way you get damped oscillations. So for nu equals plus or minus half, observe that these become cosines and sines exactly. When we studied the Bernoulli equation method of solving the Bessel functions, we found that for nu equals plus or minus half, the higher order terms exactly disappear. Now what about small x? For small values of x, you're going to end up getting different values for j's and the Neumann function or the Weber function. So that's going to be j plus or minus nu of x is approximately going to be 1/2 x to the power plus or minus nu divided by gamma nu plus 1. So what it tells us is some power of x. So it's going to be some power function, and that's as long as nu does not belong to the integers, negative integers. The reason for that caveat is when nu belongs to the negative integers, gamma functions can blow up, and they sometimes do. So you have to be careful not to have negative integer values. If you do have negative integers, also you notice that the solutions will not be linearly independent anymore, and you need to have the Neumann function. And so the Neumann function y nu x for small values of x goes like 2 over pi natural log of x. And you see the solution does blow up. As x goes to 0, this does become minus infinity. And you can do this, use this particular relation for nu belongs to R.